the deep Pacific. A realm without light. A world we once assumed was a biological desert. Yet, here, along the Galápagos Rift, life is thriving in boiling volcanic water. The question is not just how it survives. The question is how it exists at all. We are on an expedition to a place that fundamentally rewrote the rules of biology. To find the answer, we must journey 2,500 meters down to a place where the sun has never reached, and where the pressure is over 250 times that on the surface. This is the abyss.
Stand clear of the hook.
Our vessel is the deep submergence vehicle Alvin. I am inside a titanium sphere just 2.1 meters wide. It is the only thing protecting us from a force that would crush a human instantly. The descent takes over an hour and a half. We fall through the sunlit world, the vibrant blues of the photic zone. Past 200 meters, the light fades to a deep twilight. Past 1,000 meters, there is nothing. Only the comforting hum of the submersible's electronics and the darkness outside the tiny viewport. We are now entering a different planet. The temperature of the ambient seawater outside is barely 2 degrees Celsius. It is a landscape of perpetual night, carved by immense geological forces. This is not a passive seafloor. It is a birthplace. The Galápagos Rift is a divergent plate boundary. This means the Earth's crust is actively being torn apart. The Cocos Plate moves north. The Nazca Plate moves south. And in the gap between them, new Earth is forged. Magma from the mantle rises, creating fresh basaltic rock. It is a world of volcanoes, fissures, and superheated geology. But it is sterile. Or so we thought. For decades, our understanding of life was anchored to a single equation: photosynthesis. Sunlight provides the energy for plants. Animals eat the plants. Everything, from the smallest plankton to the great blue whale, was ultimately powered by the sun. This deep, cold, dark environment breaks that rule. There is no sunlight. Therefore, there should be no complex ecosystem. The maps show us ridges and valleys of volcanic rock. The sonar paints a picture of a harsh, jagged landscape. This is a world built by fire, not by light. As we drift over the seafloor, our lights cut through the gloom. The landscape is alien. Pillows of black lava, frozen instantly by the cold seawater as they erupted. Fissures and cracks spiderweb the rock. It is desolate. A vast, cold, pressurized desert. And yet, something is wrong with that picture. Our instruments begin to register an anomaly. The water temperature is changing. Not gradually, but spiking. We are approaching a source of impossible heat. The rift is alive. The scientists on the first Alvin dives here in 1977 were not looking for life. They were geologists mapping this new volcanic terrain. They were expecting to find rock, cold water, and nothing else. What they found instead was a miracle. It was a discovery that sent a shockwave through biology, geology, and even astronomy. It suggested that the requirements for life were not as rigid as we believed, that life could exist in the most extreme places we could imagine.
This environment, this abyss of fire, operates on a completely different set of rules.
It doesn't rely on the energy streaming down from the sky. It relies on the thermal and chemical energy bleeding out from the heart of the planet itself. As we navigate the Rift Valley, the water around us becomes cloudy. It is not sediment. It's a chemical haze.
We are closing in on the engine of this hidden world.
The sheer existence of this place forces us to ask a fundamental question. If life can thrive here, in total darkness, under crushing pressure, feeding on volcanic chemicals, where else might it be hiding? That chemical haze is our guiding beacon. It leads us away from the dead, cold basalt and toward an oasis.
Through the viewport, a shape begins to form in the floodlights.
It is not rock. It is a dense, shimmering thicket of life. A sight that should not exist. They are here. Hundreds of them. Great white tubes, clustered together like a surrealist's garden. Some stand as tall as a human, rooted to the volcanic rock. From the top of each tube, a vibrant, blood-red plume unfurls into the water. These are the giants of the rift, Riftia pachyptila. They wave gently in the chemical-rich currents, filtering the water. But look closer. The entire scene is teeming. Swarms of ghost white crabs, eyeless, scuttle over the tubes. They are picking at unseen morsels. There are beds of mussels, their shells stained by the mineral-rich water. Strange, pale anemones and delicate, wispy creatures that scientists dubbed spaghetti worms and dandelions. It is a complex, three-dimensional community.
A metropolis in the dark.
This is the Rose Garden, as the first explorers called it. A place of stunning, impossible beauty. And it is all built on a foundation that defies our understanding of biology. How do they eat? This is the central mystery. Let's focus on the tube worm, the anchor of this ecosystem. When biologists first dissected one, what they found was even more baffling. It has no mouth.
It has no stomach.
It has no digestive tract whatsoever. It is an animal weighing several kilograms with no apparent way to ingest food.
How does it fuel its enormous growth?
The answer is not on the worm, but inside it. Its entire body cavity is packed with a specialized organ, and that organ is filled with bacteria. Trillions of them. This is not an infection. It is a perfect, ancient partnership. A symbiosis. The red plume, which looks like a gill, is not just for breathing oxygen. It's an incredibly complex filter. It absorbs oxygen from the seawater, but it also deliberately absorbs a chemical from the warm vent water, a compound that is lethally toxic to almost all other life. Hydrogen sulfide, the smell of rotten eggs. The worm's specialized blood, rich in hemoglobin, binds to both oxygen and this poison. It then transports these two chemicals safely down to its internal bacteria. And those bacteria, they are the true engine of this hidden world. They are the producers. They are the plants of the deep. This is chemosynthesis. Instead of using sunlight for energy, these microbes use chemical energy. They breathe the hydrogen sulfide. They oxidize it, stripping it of its energy. And they use that raw energy to do what plants do. They fix carbon. They take carbon dissolved in the seawater and turn it into sugars. They create food from scratch using only volcanic chemicals and dissolved oxygen. The bacteria feast on this chemical energy, and in return, they leak sugars and nutrients, feeding their host worm from the inside out. The worm is, in effect, a farmer, harvesting its own internal crop. Every single animal we see here depends on this bacterial foundation. The crabs scuttle across the rocks, grazing on mats of these chemosynthetic bacteria. The mussels filter feed, drawing in bacteria floating in the water.
The food web is complete.
But it is a web woven entirely from chemical energy. The energy source is not the sun, 93 million miles away. It is the Earth's own internal heat, manifesting as a chemical poison. This is not an ecosystem that imports its food from the sunlit world above.
It is not living off the marine snow that drifts down.
That is a starvation diet.
This is a primary production zone.
It is a self-contained, self-sustaining world. The discovery of this process, chemosynthesis, was a profound revelation. It demonstrated that life's ingenuity was far greater than we ever imagined. It opened a new chapter in biology, proving that life does not require light. It only requires a source of energy. And the deep ocean we were about to learn was full of it. The Riftia worms and their symbiotic bacteria are the result of this deep-sea engine.
They are not the engine itself.
The scientists who first discovered the rose garden in 1977 knew this. The warm, shimmering water was a symptom, a clue that the true source was nearby. They were hunting for the geological heart of this system. On our own dive, we are following that same chemical trail. Our instruments are our guides. We move Alvin away from the garden, and the external temperature probe begins to climb. It rises past the gentle warmth of the worm field. 20 degrees Celsius, 50 degrees, 100 degrees. The water outside the viewport is shimmering, distorted by the heat. This should not be possible. We push forward, our floodlights cutting through a haze of particles.
And then we see it.
It is not a garden. It is a fortress. A tower of rock. It rises 10, maybe 15 meters from the seafloor. A Gothic spire, black as night, built by minerals. And from its peak, a furious, opaque cloud is billowing into the ocean. It looks exactly like the smokestack of a locomotive. But this is not smoke, and it is not fire.
It is a torrent of superheated, mineral-rich water.
Oasis is a black smoker, the geological engine that connects the planet's molten core to the deep ocean. The first explorers were stunned. They cautiously extended Alvin's robotic arm. They pushed its external temperature probe directly into the heart of the plume. The reading was 350 degrees Celsius. That is water hotter than molten lead. At the surface, it would be explosive steam. But down here, the crushing pressure, 250 atmospheres, forces it to remain in a bizarre, superheated liquid state. This is the engine. It is the planet's plumbing. We are witnessing a vast hydrothermal cycle in real time. It begins kilometers away with cold, dense seawater at just 2 degrees Celsius. This water seeps down into the new, fractured volcanic crust of the rift. It penetrates for miles down toward the magma chamber. As it gets closer to the Earth's mantle, it is heated to extreme temperatures. This hot, acidic water becomes a powerful solvent. It strips the surrounding volcanic rock of its minerals: iron, zinc, copper, and critically, sulfur. Now superheated and buoyant, this mineral-rich fluid rockets back toward the seafloor. The moment this 350-degree fluid hits the 2-degree seawater,
it is a violent thermal and chemical shock.
the dissolved minerals instantly precipitate, crystallizing out of the solution. It is the iron sulfides that create the black smoke. And over centuries, these same precipitating minerals build the chimney itself, particle by particle.
This is the source.
This violent, toxic, superheated fluid is the precise chemical cocktail that the bacteria from Section 2 need to survive. The black smoker is the fountainhead. It is the primary vent gushing the hydrogen sulfide, the food, that fuels the entire chemosynthetic food web. The rose gardens we saw earlier are not located at these violent, scalding vents. They can't be. They would be boiled alive.
They are clustered on the periphery. They thrive where this superheated, toxic water has mixed with the cold, oxygen-rich seawater, creating the perfect Goldilocks zone for life.
It is an ecosystem built on an exquisite chemical balance.
It needs the lethal poison from the smoker.
And it needs the life-giving oxygen from the ambient ocean. But there is a profound catch to this entire system. This volcanic plumbing is not stable. The Earth's crust is constantly shifting. Fissures clog with minerals. The magma chamber below moves or cools. A black smoker vent, the life support for an entire metropolis, can be born in a decade and die in a year. When the vent turns off, the flow of hydrogen sulfide stops. The food chain is cut. In case the bacteria die first. The giant tube worms, starved of their internal partners, quickly follow.
The crabs and mussels vanish.
Within just a few years, a vibrant, teeming oasis becomes a silent graveyard. All that remains are the empty, chalk-white tubes, a ghostly monument to the ephemeral life that once thrived here. This is not a static world. It is a world of boom and bust, entirely dependent on the whims of geology. Life here must be tenacious. It must be opportunistic, constantly sending its larvae into the dark, riding the currents. It is a desperate search for the next, newly formed chemical oasis. This ephemeral, violent cycle of life and death, driven by geology, is not just a curiosity. The discovery of this entire system, here at the Galápagos Rift, sent a shockwave through science. It was more than just finding new animals. It was finding a new, independent way to live. This discovery redefined life. Before 1977, our definition of a habitable world was rigid. It required a star, like our sun. It required photosynthesis.
The Galápagos Rift proved that life was not a slave to the sun.
Life is a slave to energy gradients, in whatever form they take. Chemosynthesis revealed a second, parallel biosphere on our own planet. One running not on photons from the sky, but on chemical energy from the stone. It fundamentally expanded our definition of habitable. This immediately led scientists to a radical new hypothesis. Not just about where life is, but about where it began. What if life didn't begin in a warm little pond on the surface, as Darwin famously speculated? The surface of the early Earth, 4 billion years ago, was a violent place. It was scorched by intense ultraviolet radiation and bombarded by asteroids. But the deep ocean, the hydrothermal vents, would have been a perfect, protected sanctuary. The vents had all the ingredients. They provide liquid water, which is essential. They provide a powerful, continuous source of chemical energy, like hydrogen sulfide and methane. And their complex mineral structures, the black smoker chimneys, are filled with tiny microscopic pores. These mineral-rich pores could have acted as the first cells.
They could concentrate the chemical building blocks of life
And provide the catalytic surfaces needed to spark the first metabolic reactions. This is the hydrothermal vent hypothesis for the origin of life. It suggests that the first life on Earth was not a photosynthesizer, but a chemosynthesizer. It was an extremophile, born in darkness, powered by the Earth's internal heat. The life we see at the Galápagos Rift today, then, is not just an oddity. It may be a living echo of our own deepest, darkest origins. This blueprint doesn't just apply to Earth's past. It applies to our future. it has become the central focus of astrobiology.
The search for alien life.
For decades, we searched for life by looking for planets just like our own.
We looked for the Goldilocks zone, the right distance from a star for liquid water to exist on the surface.
The Galápagos Rift discovered blew that concept wide open.
A planet or moon doesn't need a sun to host a liquid ocean.
It only needs an internal heat source, a geological engine,
To keep water liquid beneath a protective shell of ice.
And suddenly, our own solar system looks much more promising. We look at Jupiter's moon, Europa.
Its surface is a shell of fractured ice, miles thick.
But we know from magnetic field data that beneath it lies a vast, salty, liquid water ocean. An ocean containing more water than all of Earth's oceans combined. Europa is constantly squeezed and stretched by Jupiter's immense gravity. This tidal friction creates internal heat. It is almost certain that Europa's rocky mantle is geologically active.
It is almost certain that Europa has hydrothermal vents on its seafloor.
The ingredients are all there. Water, chemical energy, a protected environment, the same ingredients that fueled the rose gardens on the Galápagos Rift. The same is true for Saturn's moon, Enceladus. The Cassini spacecraft flew through plumes of water ice erupting from its south pole. Analysis showed they contained silica, hydrogen, and methane. That is the chemical signature of active hydrothermal vents right now. The deep Pacific, this world of volcanic fire, has become our template. It has taught us how to search. It has taught us what to look for. If we one day find life on Europa or Enceladus, it will be a direct intellectual descendant of the discovery made right here in the dark. It is perhaps the most profound legacy of this one, isolated rift. It has forced us to reconsider our place in the universe. It suggests that life is not a fragile miracle unique to our blue planet,
but a tenacious, opportunistic, and perhaps inevitable chemical process.
Ready to ignite wherever the right energy meets water.
The abyss, once a symbol of the unknown and the void, is now a cradle.
This journey to the Galápagos Rift has shown us that our planet's creative engine is not just on its sunlit surface,
but deep within its fiery heart. These oases of life, fragile and ephemeral, remind us that the Earth's capacity for ingenuity is boundless. And in understanding this deep, interconnected web, we find a new, more profound responsibility to protect the one planet we know, in all its hidden, magnificent complexity.